email is not opening. Academic calendar. TCC exam and course grade entry 30th 11 to 18th 12. Oh, I see. Okay, which means that we can do the assignment vivas after your exam. Will that be okay for you? First week of December?
Yes, sir.
Yes, sir.
Okay, let us do it then. What we can do is after the final exam is done on 30th, the first week of December we will do, because 12th is when I need to submit the grade. Sorry, 18th is the last date for me to submit the grades. So I'll have enough time to consolidate and discuss and all that. Oh, no, 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 no. This is 2023. I'm sorry, I'm sorry. I need to look at 2024 calendar. Just a second. Sorry, this is a mistake. Academic calendar.
I think it is 12th, sir.
12th of December, huh? How do you know?
Yes. I think in reinforcement learning, Salah Bhatnagar sir told that 12th is the final date to put grades. We have a project pending there in reinforcement learning also.
Okay. So there's this link, it's not opening there. Desert of Science. Yeah, I'm just opening. Hold on. Yeah. Course grade entry 13/12/2024 is the last date. Yes. Yeah. Okay. 13th is the last date. Even then, I think it's enough for me if I have 1 week. So yeah, let us do it on the week of 2nd December. 2nd to 6th December is there. No, we will do it. We'll do the Viva then. Okay, I think that is okay. Okay, Chandan, that's it. Yeah, I think I'll continue with the class.
So what is the format of the VIVA exam going to be? I mean, how much time is that going to take, and what will be the schedule?
We will let you know all of that. See, I'm thinking of about 20 minutes per group, or rather half an hour per group. And we have 20 groups, no? We are like 4 of us, 3 TAs and myself. We will make 5 groups per instructor, and we will spend half an hour with each of the groups and then we'll evaluate. That is the scheme that I'm thinking. Schedule, I will let you know. Okay, maybe late evenings or weekends, something we will make, so that it is beneficial for all. That we
Sure.
can adjust, no problem. Yeah, whatever works for all of us.
I just wanted to request for some flexibility, as I will be traveling due to some official work. So I'll be in a different time zone at that time.
Ha. No, okay. So see, those requests we can always accommodate, no problem. Yeah.
Sure. Thank you.
Okay. So shall we get back to the business? Shall we start?
Sir, one question I had.
Uh,
This is something related to the quiz 5 we just did. So if you allow, I wanted to ask a question.
Tell me, what is it? Quickly.
So, sir, there was a question. It says in DDPM, the variance schedule alpha t for each time step is carefully designed to satisfy which of the following criteria? The answer marked is it should increase gradually to prevent complete information loss in early steps. But as per my understanding, like alpha t is the product of from alpha 1 till that particular time.
No. See, that we called as alpha bar. This is the
Okay.
variance schedule alpha.
But even alpha should reduce, right? Because we want the variance to increase as we go forward in the steps.
Variance should reduce, no?
Variance is 1 minus alpha t, right?
No, alpha is what we called as the variance, isn't it? In our treatment.
I supposed it was 1 minus alpha.
Sir, like
Once.
alpha, we are drawing it from a zero, from the samples from 0, 1 space, right?
No, they are simply linearly varying. Let me just check it once. Hold on. these are small. Alphas are so beta 1 minus alpha would increase. So which means alpha should decrease gradually, right? What was the option that was there?
Selected option was alpha increases. The correct option was marked as alpha should increase.
No, 1 minus alpha should increase.
Yeah, I mean, so the last option said that
The
alpha should
variance,
gradually decrease.
yeah, that should be the correct one. Because because the variance was 1 minus alpha, right? The variance term in xt, that is 1 minus alpha. The variance should gradually increase. That's correct.
So variance should increase eventually because we want the final x of t of normal distribution, correct?
Yeah. The thing is, only when the variance slowly increases, you can guarantee that the Markov chain converges to a normal 0, 1. So variance should gradually increase. Chandan, are you there?
Yes, sir, I am there. Yes, sir.
So the question said variance schedule alpha t.
Yeah, variance schedule, I mean, of course, variance schedule is 1 minus alpha, but yeah, the parameter is alpha. So variance schedule, alpha, see if you are looking at alpha as the variance schedule, then the alpha should gradually decrease.
Yes, sir. I'll make the necessary change. Yes, sir. So, yeah, beta should increase basically. Yeah.
Just a thing, sir. In the option, it says it should decrease exponentially, the one that is being debated right now. So is it supposed to really decrease exponentially, or was that
Chandan, isn't there an option that would say it would linearly decrease?
No, sir.
No, sir. Sir, I really have no access to the quiz. I really don't know what is the question.
Chandan, I have pasted the screenshot in the chat. If you could have a
That's
look.
okay if there is no linear decrease option, you can just
decrease option will give it to.
Yeah. It should be. See, yesterday what happened as I looked at the quiz and there was beta there. I told them that beta is not something that I have used. So change it to alpha. So I think they just changed beta to alpha without changing the options. Guys, what can I say? See, I told you to change beta to alpha in a meaningful way. Just not replace alpha beta by alpha. Right? If alpha is 1 minus beta, then the options have to get flipped,
options has to be flipped. Yeah.
Anyway, so ignore that question, add +1 to everyone. Okay.
Sure. Yes, sir.
Thanks for flagging it out.
Yeah.
Sir, one more question. So we said that we are choosing alphas from 0 to 1, but on what basis are we selecting? Like, what is the predefined logic for that?
I told you in the class already, in the previous class, it is designed in such a way that the forward Markov chain that we construct has to be designed in such a way that the stationary distribution converges to normal 0, 1. Okay? So that is why the variance has to slowly decrease. And also, if you look at it, it's alpha.
Variance has to slowly increase.
What do you call by variance?
1 minus alpha.
If you call 1 minus alpha as variance, then it should increase. Yeah, of course. Depends on what you call by variance. So it is if it's alpha, then the alpha should gradually decrease, which means that 1 minus alpha should increase. Okay. That is what you have to implement in your assignment also, right? And talking of assignment, I have made assignment 3 up, right? Last week itself I did it. So hope you have started working on it. When is the deadline for assignment 3? When have I kept it?
18th, sir.
Okay, then you should have started it already. Okay. Anything else? Shall we get started with the class?
Okay. Can I take leave, sir?
Oh, yeah, okay.
Yeah. Thank you, sir.
It says working offline to me. Do you see my screen?
Yes, sir.
Yes, sir.
I don't know why it says you're working offline. Okay, anyway. Okay, let's start. See, today's agenda is that we'll be discussing some self-supervised learning techniques. Uh, so, which are special cases of these broad learning methodologies called representation learning. Okay. So what is representation learning? I had given some introduction in the previous class. So given some data that is an IID from a distribution, what you want to learn is a function f theta from the data space to some latent space z, okay, where the dimensionality of z is much less than the dimensionality of x. Now we seek some special properties on z. So the properties that we seek is in such a are that the representations are, by representation I mean z, okay, the projection that you learn on data, and we need that to have some desirable properties, such as if you use z instead of x, then the amount of supervision that you need is much lesser, and the z becomes much robust than x and all that. Okay. Now, learning representations can be done in two ways. Right? One is the generative way, where you learn a latent variable model and use the latent space as representations. We have seen this all throughout the course, right? And I've asked you to do this in your assignments as well, where any latent variable model that you learn uh, implicitly have this capability of learning representations, because when you do posterior inference, which is get samples from P of z given x, then you are automatically doing representation learning, because z, the latent variables that you get from a latent variable generative model, can be seen as representations. Okay, that is one way to do it. The other way to do it is what we will see, which is a non-generative way, also called self-supervised learning or contrastive learning way, okay, where the fundamental idea is that you define a pretext task. Okay, what is a pretext task? You solve some other task using data. Note that in all the representation learning literature, you don't have labels. Okay, this is label-free learning. Okay, so now when you don't have the labels, you define some pseudo tasks. Okay, where you define some pseudo labels and you ask a neural network to solve some pseudo task. Okay, and the intermediate representations of the pseudo task solver is what you take as representations for data. The examples for pseudo tasks are, if you are looking at like learning representations for images, then you take an image, rotate it with some angle, by some angle, and ask a neural network to predict the angle of rotation. So that can be one pseudo task. The other pseudo task can be that you have an image, you add some noise to it, okay, and try to classify between the noise and the data, and you take the intermediate representations of that classifier as your representation, and so on. Okay. The other thing can be that you take data and you mask it and try to reconstruct the data back. That is one other way to define it. So these class of methods are called self-supervised learning techniques. Now we will go deeper into it and see why should these methods even help in learning good representations, and also some famous examples of how to do it. Okay. In fact, the language models, right, like BERT, etc., also uses the same kind of technique, okay, to learn representations on data. Any questions on this so far? Hello, am I audible?
Yes, sir.
Any questions?
Maybe we'll cover it later. Just a query here. The pretest tasks are defined, I mean, like based on how it should perform in the end, right? I mean,
Well, not necessarily. Not necessarily. See, I will tell you what the fundamental idea behind this thing, and in fact, how to define a pretext task is a question that people have been asking, right? And different ways have been looked at. Okay, we'll talk about it. We'll talk about it. Yeah.
sure. Thank you.
Okay.
Hello, sir.
Yes.
I have a query. Like, is there any methodology like if we define this pretext, then the embedding will have some kind of structures which will be helpful for other features. Like what I mean is, if suppose I use the pretext as in painting, then it will be helpful in classification or segmentation. But if I use some other pretext, then it won't be much helpful for classification or any other segmentation task. Like, are there any such kind of things?
Not theoretically, but there are some empirical ideas on what sort of pretext task would help. We will discuss all that. Just let's see. Give some time. Okay, it's not there here. Where did I do NCE? Just a minute. I'm just looking for my. Hmm. Just want to see if I did it the last year and if there is. Okay, I've done it. Just a second. Huh? 2 minutes. I have to. Okay. The fundamental idea for all self-supervised learning techniques come from this very nice paper, okay, very nice methodology that came up, which was called noise contrastive estimation. Noise contrastive estimation, also abbreviated as NCE. Okay, so the the basis for self-supervised learning lies here. The question that is asked is the following. Okay, suppose you have data drawn from an unknown distribution Px. Okay, so what we have is we have d that is given by x1 to up to xn. Okay, these are drawn IID from Px. The objective is to estimate the underlying distribution Px given d, right? This has been a question that we have been asking. So now how do we estimate the underlying distribution given a particular given samples from distribution, right? This is a question that we have been asking. How did we do that? I mean, so far we have looked at the maximum likelihood estimate or the minimum KL estimate, right? So both of them are equivalent. How did we do that? Start with a parametric form for Px. Call it P theta and get theta that would simply minimize some divergence metric which we call the F divergence between Px and P theta. This is what we have been doing the entire course, right? All the generative modeling frameworks that we saw were actually fitting into this framework, right? Where we minimized a divergence metric between, started with an assumption on the parametric assumption on the underlying density, called it P theta, right? And minimized a divergence metric, F divergence metric between these two. So now how do we define P theta is where we change different models. In GYAN, this P theta is taken to be the samples that are coming from a transformed Gaussian random variable. The transformation is through a neural network. In a VAE, we use a latent variable model for this, and we find a lower bound on this and then optimize this and so on. Right? We know the entire story. This is how we do it in a generative framework, right? So where we assume a parametric form p theta and find the parameters by minimizing an F divergence. So now NCE provides an alternative for this. Alternative for ML estimation. Now, self-supervised learning. So did it get uploaded? Hold on. Oh my god. I just wanted this to get uploaded to my drive so that I can access. Simply did not. Okay, so in in self-supervised learning, see what do we need? We need a representation for data, right? So when do you think data would be represented optimally? The data would be represented optimally only if you learn the underlying distribution correctly, isn't it? See, what we need is that we need to learn the underlying distribution correctly, because if we do not learn the distribution, then we are not representing the data. See, that is why the generative modeling framework, right, will implicitly give you representations, because by definition, when we have a latent variable model, the latent variables actually aid minimizing the KL divergence between, or rather F divergence between the true distribution and the model distribution, right? And therefore, the representations that we get by solving a KL minimization problem under a latent variable model implicitly gives us a representation. Now we are explicitly trying to find the representation. This is not getting uploaded. Do you know some other way to do this? Sorry about this. Has anybody used this airdrop thing between two Mac devices? Do you know how that works? Hello, am I audible?
So you can also share it between two Teams instances if you have it on both the instances. Share it to yourself.
You can just right click on the file and share, and then you'll see airdrop there.
Oh, this is very good. Okay, it just came to my Mac. Nice. Apple devices are what they are for a reason, no? Extremely good. Okay, I just got what I wanted. Thanks. Okay, so you see my screen, no? Do you see my screen?
So there's a file transfer pop-up.
No, I'm writing on my usual stuff.
Sir.
No?
No.
Oh my god, something happens. Let me know when you can see my screen. Can you see my screen?
No, sir.
Not yet, sir.
Why is it not coming?
Yes, it is visible now.
I'm writing. Do you see that? No.
No, it is stuck at NCE provides an alternative for ML estimation. I think it's stuck there. Yeah.
Can you please let me know if it's coming?
Yes, sir. We can see, suppose that you wrote.
Okay, so hopefully it will not misbehave. Okay. Now we have, okay, noise contrastive estimation provides an alternative for ML estimation, right? Where the goal is to estimate the underlying distribution, okay? Now, how does NCE does this? Now we have data that is x1, x2 up to, let's call it xn, that is drawn from px. This is what we need to estimate, okay? And we define a noise distribution. Noise distribution P n and draw samples from it.
Okay.
Let's call this as dn, which is maybe we will change the notation. There are too many n's that I'm using. There are t number of samples. And you have n1, n2 to np. Okay, these are drawn from Pn, IID from Pn. So you understand what we are doing. We have the data distribution that we have been given. Okay, we define a noise distribution Pn and draw samples from it, which are denoted by n1 to nt. Okay, now define an estimator. Define an estimator Jt parameterized by theta as follows. How do you define J theta? J t theta, t because it depends on t number of samples, it's given by 1 over 2t sigma over t log of h theta of xt plus log of 1 minus h theta of nt where h theta of h theta, you can take both xt and nt, so h theta is a function parameterized via neural network. So h theta is a function that takes data from d-dimensional space and maps it to 0, 1.
So the summation is common, right? For both.
The summation is common for both of them, yes. Okay, so this j t theta, okay, is called the noise contrastive estimator. Okay, this is the noise contrastive estimator. Okay, okay. Now there are multiple claims that we should make. Okay, now the first claim that we do and show is the following. Claim 1 is that j t of theta, should we do it the other way around? Just a second, let me just think how to best present this. Okay, so maybe I'll tell you this and then, okay, claim 1 is j theta of theta, okay, jt of theta, the noise contrastive objective. Before we move on, let me just tell you this. See, this j theta can be computed, right? Suppose you have h theta as a neural network, j theta can be computed and you can actually backpropagate through that neural network to find theta. So basically what we will do is represent j theta using a neural network, okay, and find your theta star as the minimizer of the objective function over theta. Okay, we can do this, we can solve this optimization problem. So this theta star we get is the NCE estimate for data. Now the questions that we should ask now is, why should this theta star, or rather why solving this object optimization problem lead us to, okay, so let me write it down. So question, why is j theta a good estimator for px? Okay, so now you remember that what we actually need is an estimate for px, isn't it? What we are trying to do is learn the underlying distribution px. That is our goal. Now I somehow defined some objective function, right, that we would like to solve. The question is, why would solving this objective function lead to a good estimate for px? Are we good so far? Let me repeat what we did. So we are given some data, okay? Yeah, we should line here. We are given some data, and we define another distribution called the noise distribution, from which we know how to draw samples. We draw equal amount. Also, you should observe that the dimensionality of x, okay, is the same as the dimensionality of n. So noise and the data both have the same dimensions here. So we draw n noise samples, okay, and we define an estimator or an objective function that would involve the data samples xt and the noise samples nt, okay, and there is another function h theta, and h theta is approximated using a neural network. And once we use this objective function, so now what is happening actually is that there is a neural network, okay, and this neural network will either take x or n as input and give you 1 or 0 as the output, correct? It will give 1 or 0 as input, right? I mean, this is our h theta function, correct? Now and what is the objective? Objective that we are using is j theta here. Now the question is, why should solving, the claim that we are making here is that if we do this, then we would implicitly learn px. Is the story clear so far? Now we should see why solving this sort of an objective using this technique should give us should implicitly estimate px. That is what we are going to answer now. But is the story clear so far? What we are trying to do?
Yes, so only DN, we're not sure how it is.
Only what?
DN.
It is some
totally
distribution.
Random?
Yeah, it is totally random. It is some distribution that is not px. So we will write that. So now also Pn is just a distribution that is not the same as px. Okay.
Sir, if the noise is input, then h theta will return a 0. And
let's see what it returns. Okay, but yeah, for now it's simply a function from the data or noise space to 0, 1.
Okay.
All right, is that okay? Okay, so let us see some properties of this estimator now. What is this estimator actually is doing, and why should it get why should it estimate the underlying distribution? Okay, now let's look at the properties of the NCE estimator. So this is called the NCE estimator, okay? The first one, which we will see, which is important, is that j theta is equivalent to solving a binary classification problem between the samples of Px and Pn. This is the first property. What we are saying is that this complicated looking, or rather this estimator that we have is nothing but solving a binary classification problem between the samples of Px and Pn. Okay, so let us look at why this is the case. Now create a supervised data set. Supervised data set combining D and Dn, okay, as follows. Let's call it some S, the new data set, supervised data set. Now that has samples like this. You have U, comma, let's call that U1, comma T1, U1, comma T1, U2, comma T2, U2T, comma T2T, okay, because there are T samples of noise and T samples of data. We are combining them both. Okay. Now, how are we defining this? Now, Ti is equal to 1 if Ui comes from Xi, okay, and Ti is equal to 0 if Ui is from Ni. Do you understand what we did? What did we do? We just created, so that we had the T samples of noise and T samples of data. We combined them both, okay, and created a data set such that whenever we have data samples, we gave it one label, and whenever we have noise samples, we gave that another label. Is that all right? Hello, are you there?
Yes, sir.
Okay. Now what we do is the following. From the above, we have what is the posterior of U given T equal to 1? What is this equal to?
Data px.
This is px, correct? Yeah, good. So now the distribution P of U given T equal to 0 is Pn, right? P of T equal to 1 is equal to, what about the priors? T equal to 0, both of them are equal to half, because we have T samples of data and T samples of noise, correct? Now with this, let us find the posterior of labels. So what are labels here? Labels are T, correct, given data U. What is this? Which is probability of P equal to 1 given U. What is this equal to? It is equal to P of U given T equal to 1 divided by P of U given T equal to 0 times P of T equal to 0 plus P of U given T equal to 1 plus P of, into T equal to 1. Here you have P which is
T
all
equal
right.
to 1.
P of T equal to 1, no?
Yes, sir.
Right. Yeah. This is base law, right? Now because all the priors are equal, we can just cancel the priors. All of these are half. Just cancel them. So this is equal to P of U given T equal to 1, which is Px divided by Pn plus Px. So what is this? Is the posterior of T equal to 1 given U is given by this. Is that all right? Are we good so far?
Yes, sir.
Okay. Now, it's actually called the optimal Bayes classifier between the samples of these two. Which decides upon the ratios of posteriors, okay, ratios of class conditional densities. Okay. Now, suppose we model, so in all classifiers, what do? We model the posterior of the label given data, right, using a neural network parametric function. Parametric function h theta of u, right? So what is happening? We are modeling p of t equal to 1 given u using some parametric function. See, this is exactly what we do in all supervised learning, isn't it? We model that using some parametric function h theta of u, which can be a neural network. Okay. Now, t given u, can somebody tell me what sort of a random variable t given u is? What is what is the form of t given u?
Indicator random variable?
It's indicator random variable. All binary classification, all binary random variables, right? They are is a Bernoulli random variable. It's also indicator random variable. What is a Bernoulli random variable? Bernoulli random variable is a random variable that takes one of two values with probability p and 1 minus p. Coin toss is one example. Okay, it's a Bernoulli random variable with the parameter h theta of u, isn't it? I mean, h theta of u is the success probability of this Bernoulli random variable t given u. Okay, that is what it is. Now, suppose we want to find this h theta of u by finding out the, by maximizing the likelihood. So now let's write the maximum likelihood estimate.
Sir, how is this parameter h theta of u?
See, that is what we have done. No, this h, we have modeled p of t equal to 1 given u using a parametric function. So this h theta of u is giving you that probability of t being equal to 1 given u. Okay. In fact, right, all binary classifiers does the same thing. All binary classifiers, what do? The output of it is actually the estimate for the success probability of a Bernoulli random variable, which is the conditional random variable of label given data. Correct? Okay, so let us look at the ML estimate, maximum likelihood estimate for this Bernoulli random variable t given u. How does that look like? The likelihood function L theta for a Bernoulli random variable, in fact the log likelihood, not the likelihood, for t given u, call it L theta, can be expressed as follows. So L theta is equal to, we have log of products. What is the log likelihood? We know that, no, log of p theta xi t, hold on, that is log likelihood function, it is sum of log of p theta of xi. This is the definition of log likelihood, no? Or I. Okay. We have written that as t here. I is the sampling index. In the case of Bernoulli random variable, what is p theta? P theta of the variable that we are looking at is p given u, right? So what is the distribution of a Bernoulli random variable? If you write that as an indicator random variable, then it is to the power of p. Or rather, write that as when t equal to 0, product of these two.
There it is p to the power t plus 1 minus p to the power 1 minus t.
Yeah. H theta, right? Yeah, that is what it is. So you have the distribution of Bernoulli random variable is given by the success probability is h theta, no? Which is h theta of u to the power t plus 1 minus h theta to the power 1 minus t. Yeah, this is the definition of the likelihood of a Bernoulli random variable. So just substitute this here. So log likelihood will be equal to sum of, or I, we have t times log of h theta of u plus 1 minus t times log of 1 minus h theta of u. Okay. Now if I split this I into indices where whenever t equal to 1, this will become log of h theta of xi, right? Because whenever t equal to 1, we have xi as the data point. Whenever t equal to 0, we have it to be n. So this is log of 1 minus h theta of ni. That's it. Okay. So now what is this equal to? This is actually equal to 2 times 2t times jt of theta, which is our NCE estimate. Okay. Right. So what did we show so far, notwithstanding the math, is that we showed that j theta is equivalent to solving a binary classification problem between the samples of px and p theta. That is what we showed so far. How did we do that? We first created a supervised data set where two classes were created, one for the noise and one for the data. And we looked at the optimal base classifier as the estimator of the posterior of the labels given data, right? And we modeled that as a binary Bernoulli random variable using a parametric function h theta. And we just simply obtained the maximum likelihood estimate for the posterior, which turned out to be simply the NC estimate, right? Then what are we saying? The summary is that NCE is a binary classifier between these samples of Px and P theta. Is it all right? Any questions on this? Okay. Okay, so this is good. So what we are actually doing in noise contrastive estimation is that given data we just define some noise distribution. Okay, so we take samples from some noise distribution that is not the data distribution and trying to learn to classify between them. Yeah, Vivek.
But somehow it seems the success depends on how well we give it the noise. So how do we ensure that the entire, so how big is non-data distribution? Like it is the entire universe, right? What can we give them?
Yes, that's good. That's a good question. That's a good question. We will answer that. We'll answer that eventually in this class. In fact, not to make you wait. See, the point is, it's very difficult to come up with that noise distribution, and that is why you might have heard this term called hard negative mining, right? In contrastive learning or self-supervised learning techniques, there's this term called hard negative mining. Okay. Yeah, so that is actually this. How do you sample PN is a question that people have asked. We will discuss that briefly later. Yeah, but what I wanted to convey was this. NCE is a binary classifier between these two samples, not P theta, sorry, this is PN. PN, okay? That is what it is. Okay. So now, okay, fine. You just let us classify between the samples of the data distribution and some random distribution. So now what, right? Now comes the most interesting part. What we would show is that solving this, j theta attains its optimal, okay, only when this h theta implicitly estimates the underlying distribution is what we will show. Okay, that is something that we will show. Shoot. Just thinking, should I have to do it now or just take a break and come back and do it? Shall we take a break? Some 15-20 minutes break and come back? Okay, I think you have been writing quiz and all that. Let's take some break. So this is 10:50, 10:53. Let's get back at 11:15 and continue from here. See you in 15-20 minutes. Hello? Shall we resume?
Yes, sir, we can hear
Sir.
you.
Shall we continue?
Yes.
During the break, I was just reading some news, and do, do you know the name of this Elon Musk's son? People do
Some
all
code,
kinds
sir.
of
It's
crazy
some
things.
code.
Huh?
It's
No,
some.
it's not code. I mean, it's some XA12 or something, right? No, no, like imagine the plight of that kid when he goes to school, right?
Yeah.
Actually, not very a big fan of these complicated. I mean, even today, no, young parents in India, they are also doing these weird things. No, they see, because naming happens only once in lifetime, and they want it to be exotic. They name children with all kinds of random things. I keep thinking, especially when these kids grow to be like older adults. How do you
Yeah.
call them with such weird names?
They'll be traumatized, sir. That's all will happen.
And so many names that mean nothing. Simply they'll see somewhere and they'll say that it's a Sanskrit name. I mean, studied enough Sanskrit to identify that most of these names are not Sanskrit. So what to do?
Right. At
Anyway.
least in India, people base the names on like movies and all those places. But this pyramid kind of name, ZA12, some 1 to 14, I don't know what it is.
Anyway, none of our business. Okay, let's get back. Yeah, so we were looking at noise contrastive estimation, and we saw that it's a binary classifier between samples of two distributions. Okay. Okay. Now we will continue. So now, okay, fine. The question is, fine, you do a binary classification between these two distributions. What's great about it, right? There is this very nice result that would say the following. So property 2 of noise contrastive estimation is that we have j theta to be equal to 1 by 2t. So it's log of h theta on x plus log of 1 minus h theta evaluated at nt, right? This is what the loss function was. Okay. Now, law of large numbers would ensure that j theta is approximately equal to some j tilde of theta, where j tilde of theta is given by the following. It is half expectation of log of h theta evaluated at x plus log of 1 minus h theta evaluated at n, and this expectation is over the joint distribution of p, x and n. Yeah, this is what the law of large numbers says. Okay, this we know, right? I mean, if you have samples from distributions, then expectation can be approximated using sample averages. We inverted that, meaning we said that this was a sample average, right? Whatever we had in j theta was a sample average. We just converted that into t equal to 1 to 2t, converted that into expectation. Okay. Now, suppose f is given by log of that. Let p theta of x denote the distribution being estimated via NCE. Okay. So we solve this optimization problem. We are implicitly imposing a distribution on the model. Let's call that as p theta. Okay. Now, now let f be equal to log of p theta of x. Okay. Now what can be shown as that I'll just give the proof for the want of time. J theta can be shown to be equal to half of expected value of log of r f of x minus log of Pn of x plus expected half times the expected value of log of 1 minus r times f of n minus log of Pn evaluated at n. So this equivalence I will not show. I mean, this is only an algebraic manipulation. What can be shown is that this j theta can be written equivalently this way, where r, something that we don't know, where r is simply the logistic function. R of k is 1 by 1 plus e power minus k. R is the logistic function. When it involves just rewriting the equation, of j in terms of what we know. Okay. So why is this important? So again, I will state a theorem without proof, which again can be solved easily. I'll tell you how to do it, proved easily. So theorem is that. Okay. So with this, what happens is your j theta now can be written as a function of f, no? Because question?
Sir, in the first term, this r, for this function r, the argument is just fx or fx minus log Pn of x?
So it is r of f of x, yeah. So r is a logistic sigmoid, right? So it is r of f of x, right? And r of f of n minus log Pn n into n, correct. Yeah, the bracket was missing. Okay. So now you represent this entire, see, what did we do? I mean, we represented the log likelihood of the underlying distribution using some function f. So strictly speaking, this is f theta, right? And we represented the noise contrastive estimator in terms of f theta. Okay. Now this theorem, which is the most powerful theorem, that would say that the optimal value of f theta that would optimize j tilde of theta is such that f star is equal to log of px of x. This is the most important result. Okay, now the question that we are asking is the following. I'll tell you how we would get it that way. Okay, the question that we are asking is that what would be the f star, okay, that would maximize this objective or minimize the negative of this objective is the question, right? Because the only variable here is f, no? We are searching for an f, okay, that would maximize this objective. Now, what can be shown is that irrespective of what n you are choosing here, that f which is maximizing the objective j theta, non-contrastive estimator j theta is the one for which the f happens to be the log likelihood of the true underlying data distribution. Now, how do we get that? So we get that by writing this entire thing in terms of double integral, right? This expectation will be written in terms of the double integral of this thing times px into n, assuming that noise and data are independent. You write these as marginals over px and pn, okay? dx dn, and then you differentiate this integral with respect to f and put it to 0. What you will get is that the optimal f is going to be log of px. That is what it is. I mean, you need a bit of variational calculus to show that, which is beyond the scope of this particular course, and that's why I'm skipping the proof. But yeah, but the result is that the optimal value for the noise contrastive estimator is when the log of the distribution that it is implicitly imposing on the model is equal to the log of the likelihood of the underlying data distribution. Okay, this is a very powerful result. So now the summary or the take home message from this, what is the consequence of this is, summary is that one can use, or rather solving the classification problem in the NCE estimate between px and pn will implicitly learn the underlying distribution p theta. Distribution px. This is the most important result. Okay, so you understood, right? So what we are doing is, suppose we have a classifier that is built. Let's say that we take x or n to this. This is your h theta, and this will finally give you 1 or 0. Okay, trying this, what we are saying is, if you take the intermediate representations of this, okay, so let's call this as f theta of x, because as you saw, what the h theta was the logistic sigmoid of f theta of x. So whatever you get before the final layer is the logistic sigmoid. So whatever you get before the final layer, penultimate layer, or the logits, is what you call as f theta. And we know that f theta, the optimal f theta, is log of f of x, right? And what we can use, that we can write z to be equal to f theta of x as the features for embeddings or representations. That's it. So this is the result. So what we are saying is that you don't have to do anything. All you need to do is that if you are given some data, okay, define some noise, sample from it, and learn to classify between the data and the noise. So now if you do that, then you are implicitly learning the underlying distribution. Take the logics of that classifier and use those as features. See, this is what is called as the contrastive learning. Or self-supervised learning. So what is the self-supervision part here? Remember that we defined a pseudo task. Now the pseudo task, the pretext task that we defined here is that of classification, right? This is the fundamental bedrock of contrastive or self-supervised learning, okay, where it comes from noise contrastive estimation that would say that solving an optimization problem, which turns out to be classification between the data distribution and some noise distribution, will implicitly learn the underlying data distribution up to a constant. Any questions here? See, this is the idea. I mean, everything else that came after this, no, it's only as improvisation over this idea, but this is the fundamental idea actually. Any questions here? Hello, are you there? Am I audible?
Yes, sir, you are.
Yeah, okay. This is a very powerful result, right? I mean, it is saying that all you need is to simply classify between the data distribution and some noise distribution, and if you do it, please note that these results are asymptotic in the sense that this will give you an estimate for the log likelihood of the underlying data distribution only if you have enough samples. Now, as Vivek was asking before the break, now how do you know what noise distribution would help it? In fact, what can be shown while doing this proof is that the larger is the divergence between Px and Pn, the better it is to estimate the underlying data distribution. Okay. Now, getting those noise samples is very important. Now, that is why we have so many methods on how do you define the hard negatives, how do you come up with the negative samples. Okay. But yeah, so this is the fundamental idea of why should solving a pretext task, okay, or a pseudo label task should help you in learning the data distribution. Please note that this entire thing is non-generative in the sense that you can't sample points from Px from this, right? Is this clear? This is not generative, right? Not able to sample from Px. It's a non-generative. Okay.
Sir, if we are not able to generate some samples, then how can we say that we have learned the original data distribution?
And that's what we saw so far, right? See, what we showed was that, see, we are not able to sample from this thing, but solving this classification task, what we are getting is at the penultimate layer of this classifier, we are learning the log of the underlying distribution is what we just showed, isn't it? The entire today's class was on that.
Yes, sir.
Yeah. So we can learn the underlying data distribution even without sampling from the distribution is what we showed.
Sir, from this, if we connect it to a sampler, it can ideally sample it, right? I mean, we got the distribution, right? Data distribution.
No, we didn't. No, not explicitly, right? See, given an x, it will see what is this penultimate layer giving you. Given an x as an input, it is giving you log of px of x. That's all, right? It is not telling you what px of x is.
So there is no way to reverse engineer.
There is no way. No, absolutely no way. No. But what is important is that if you know log of px of x for all samples, then you know everything about the data. That is why these features are powerful. See, why do you think BERT embeddings are so? In fact, BERT also does exactly this thing. We will come to that in a while. Why do you think those are so powerful? Is because if you do this well, okay, with a large number of samples, so that the law of large number is respected, then the representations or the embeddings that you are getting from this classifier are actually estimating the log likelihood of the data. Right? That's all. So you know everything about the data. So you can use it for anything that you want. That is the idea. But you are not able to sample from here. Yeah.
Sure. Thanks.
Anything else? See, compare this with let's say a VAE or a diffusion model or a DDIM, where you will get embeddings, okay, as well as ability to sample. Right? So this generative pre-training, no, GPT. So that is an example where you have the embeddings and also the generative ability. We will look at GPT probably in the next class, right? Where you generate the embeddings, right? Or rather find an embedding space representation and also learn to sample implicitly from, together, just like a diffusion model or a VAE. In a GAN, right? For instance, in a naive GAN, can somebody tell me what abilities does it have?
The generative.
It can generate, it can't find out it can't do posterior inference. But we did see some examples, right? In your assignment, I had asked you to, did I ask you to do that or not? Like build a classifier or an inverter over the generator and solve a reconstruction task over the latent space. Did I ask you to do that?
Yes, sir.
Yeah. So you have done that, right? So now you can improvise GAN to do an inversion or a embedding extraction as well. Okay. Right. Sarvesh.
So in this case, so this f theta for this discriminator, will it be a scalar, single number? Because we are getting only one output, right? 1 or 0. So
yeah, that's a very good question. Yeah, it will be scalar, and that's why people said, okay, let's move away from this. Why only do a binary classification problem? Let us solve an n-class classification problem, which is what is called as InfoNCE. Okay, where the idea is to extend NCE to a multi-class classification setting.
so that we can get a vector of embeddings.
Correct.
Oh.
So what InfoNCE does is that it is simply a multi-class classification problem. So given a data point, xi, okay, define k noise examples or noisy examples from Pn and solve a k class classification problem. Between xi, in fact it's actually k plus 1 class classification problem and k negative samples, noisy samples. Okay, this is what InfoNCE does. The paper's name is Representation Learning with Contrastive Predicting Coding. Okay, I mean it's nothing but extension of noise contrastive estimation, okay, for a k-class classification problem. So let me just show you the paper. Give me a second. Let me share my screen and show you. Share screen. Do you see my screen?
Yes, sir.
By the way, this is the paper on noise contrastive estimation. It's a very nice paper. Okay, it's very old, but this is the one that noise contrastive estimation, a new estimation principle for unnormalized statistical models. Please look at this paper. It's very good. Okay, like 2010 it appeared. Okay, but it was just sort of buried because this could not be scaled to higher dimensions because then the neural networks were not very powerful. It's a very nice paper. Okay, have a look at it. Then came the InfoNCE paper 2019, which is called Representation Learning with Contrastive Predicting Coding. Okay, so where what they do is just extend NCE for a k-class classification setting. Given a set X of n random samples containing 1 positive samples from the distribution that you want to estimate and n minus 1 negative samples from the proposal distribution, right? So yeah, so if you take a set of n samples, okay, one of them is the so-called positive sample or the sample from the data distribution, and there are n minus 1 negative examples. You define the NCE loss as the negative of the expected loss of expected value of the log of this thing. So what is this? If you look at it, this is nothing but the softmax, okay, where fk will give you the kth output of the softmax in the neural network, okay, and it is summed over all possible other samples. This is all right. This is the InfoNCE loss. Now what can be shown, just like the NCE counterpart, is that optimizing the optimal value of this fk is the one that gives you the log of this underlying data distribution. It's just simple extension of NCE, okay, for a k-class classification problem. Is this okay? Now this, okay, came in 2019 and this was extended to the contrastive learning. This was Hinton's paper, right? This was well celebrated. This is called SIM-CLR, okay, stands for Simple Framework for Contrastive Learning of Visual Representations. Now look at this graph. What they show is the following, that if you take the ImageNet top 1 accuracy, you take the representations that are given by this SIM-CLR and do a fine tuning. So now what do you do with the representations? You take those representations, and if you want to solve a classification task, just fine tune another classifier using those representations. That is how you use it. It was shown that it just beats all the existing state of the art. Okay, on the fully supervised is of course the best that you can get, right? But even with very less number of parameters on the fine tuning of the fine tuning network, you can get a pretty comparable result as what was shown. Okay, now what does this do? This is nothing but InfoNCE. Look at this expression. So this loss function that is used in SIM-CLR is nothing but the InfoNCE loss. Okay, write it as the dot product between. So what they have done is, look at the InfoNCE paper. They write this fk, right, as a dot product between the representations for the positive sample and the negative sample, and this is just the normalization constant. Okay, so what is done is the following, that given an image, they create multiple augmentations of the image by doing these kinds of things, crop and resize, and then you have color distortions, and you add some Gaussian noise and blur it out, and you do Sobel filtering and extract the edge and all that. Okay, now what they do is, given this particular image, all of these counterparts are taken to be the positive counterparts of this particular image. Okay, and then what they do is, whenever the network sees these augmentations, they want the network to output 1. See, think of it like solving a K-class classification problem where the original image and all of these augmentations are taken to be of the same class. Okay, and all the other images that does not correspond to this original image is taken to be the from the other classes, and you solve a K-class classification problem. Does it make sense?
Yes, sir.
Any questions on this?
So this one will result in K+1 vector out, right? I mean, the dimension of the
not necessarily,
the
right?
representation.
See, the way they have done is, they have taken the penultimate layer to be of some d dimensions. Okay, now the loss function will take those d-dimensional vectors and compute the dot product between those representations here. That is how they implement this FK. So you can actually customize it.
Okay. Yeah.
Yeah, because they don't implement it as cross entropy. They implement it as the dot product between the representations that have been gotten between these two. Any other question on this? And see, the fundamental idea is that of the NCE. Okay. Now improvisations have been done where instead of solving a binary classification problem, you solve a K-class classification problem. Now you represent the objective of the K-class classification problem in terms of dot products, right, or inner products between the pre-logit layers. Okay, that is proportional to, of course, the binary cross, categorical cross entropy, right? That is what SimCLR does. Is this all right?
Yes, sir, but there is no noise involved here now, right?
Well, you can see all the negative samples that you get here, right? Is actually the noise. See, if you look at the algorithm, what they do is they take one sample, okay, one data example, okay, and create all the augmentations of it and call it the positive example, okay, and then what they do is they sample randomly. I'll just show you that. See, here they say that we don't sample negative examples explicitly. Instead, given a positive pair, we treat the other two n-1 augmented examples with a mini batch as negative examples. This is the way they define the noise here.
Okay.
Right. But again, as I said, there are lots of improvisations over it. Then people came up with something called MOCO, right? Momentum update, contrastive encoding. Yeah.
So what effect does this actually have? This just tries to push away the vectors from each other. Like if you're going to say the dot
not
product.
Push away, right? So what does it do is, whenever you have the positive pairs, it will try to cluster them together. Whenever they are negative pairs, they will try to push them apart. That is what a classifier also does, isn't it?
Right. Yeah. So okay.
Right. That is exactly what a classifier does. It is trying to cluster the points that are from one category, it is trying to push the points from the other categories away. That's all. Now, what is the intuition? See, I did the math because, I mean, you might have probably known from the course so far is that I mean, I get convinced better if I'm shown some mathematical guarantees of what's actually happening. But I can give you some intuition also. So what is actually happening with all these methodologies is that suppose you know how to uh, uh, group all these examples as close to this dog image and a cat image, you know how to push the cat image away from this. You can't do it I mean, you can't do it, or rather, you can do it only if you understand the semantics of this object called dog, isn't it?
Okay.
See, if somebody wants to put this dog image and this cutout dog image into one same category, they should know that okay, this is actually a cutout version of this dog, isn't it?
Right. Okay.
Right. So that's the whole point. So now, do you recall these? These question types that we were having when we were going to school, right? One of the question types was this thing called fill in the blanks, isn't it?
Yeah.
They used to give a sentence and used to ask us to fill in the gaps, randomly mask some of the words and ask us to fill the gaps. Now you can do it only if you know perfectly what the semantics are, isn't it?
Yes. Yes.
That's the whole point. In fact, all these language LLMs today are learned using that technique, this technique only, which is which is the mass reconstruction. So you have data, you mask some parts of it and try to reconstruct it back. So which is nothing but classifying between the data sample and the noise sample.
Okay, sir. Yeah.
Right? Okay. So any other question on this?
Sir, one question.
So there is a 2 into n minus 1 images, right? What is that 2 indicates here? Is that 2 augmentations only we do per image?
No. Given an image, you take n augmentations and you sample n other random points. Right?
Okay.
So that will make it 2n minus 1, isn't it? I mean, they count from 0, that's why there are like 2 times n minus 1. Basically, it's 2n. So you take an image or a data point, you take n augmentations of it and call all of them as positive, right? And then you sample n negative samples from the data set. So that will make it 2n, no? 2 capital N. That's all it is.
Okay. Sir, and negative samples here means, can you clarify?
You need samples from the noise distribution, right?
Yes.
What is done is that you take a dog image and you take n augmentation, that will give you the positive ones.
Okay.
You need samples from the noise distribution as well. So what is done is people just sample n random points from the data set itself. We'll call them the samples from the noise.
From this dog data set itself.
Not dog. This data set has all kinds of objects. This data set has all kinds of objects. So now if you randomly do a sampling from all objects, the other n samples that you have gotten hopefully are not from the dog category. That's a good point that you made. See, what happens is these methods, especially SimCLR, has been shown to work well only if you have a very, very large batch size. Okay. Now, why is that the case? Is because suppose you have like you have very small batch size. When you take when you do sampling for negative sample with n samples with n being very small, there's no guarantee that these so-called negative examples that you get are not from the dog category, isn't it? You don't have control because we have no labels, right? But if you make our batch size to be very, very large, then what happens is if you sample a very large number of samples, then most of them will not be from the class that you are considering for this particular example. That's why the SimCLR is known to work only with very large number of examples, like very large batch sizes. Yeah. Okay. Questions on this? Yeah, Vivek.
So, one question. So, is the noise contrastive estimation the same as out of data distribution detection?
Sort of, yeah. You can view it as like outlier detection actually, yeah. See, if you are solving a binary classification problem, yes, it is outlier detection. If you are solving a k-class classification problem, then like detecting outliers from multiple distributions. That is what it is.
No, so outlier is a very specific case. What I mean is something like a out of distribution detection, which means
Agreed.
yeah,
Agreed.
okay,
Agreed.
okay,
You want to you are classifying between the
set of
samples of the data distribution and everything that is not the data distribution.
yes, yeah. So
See, that's how human beings also learn, no? If you know how to classify between, what is important, what is not important, then you have learned the tricks of the life. That's what they say.
okay, so
Okay. Okay, so let me get back to this. So as I said, there are multiple improvisations over it. So now one question that people ask is, now, how do you reduce the batch size in SimCLR? So one way to do it is that whenever you are sampling from the noise distribution, as Vivek was asking, you sample the noise points in such a way, right, that that they are very I mean they are pretty away in the representation space from the data samples. Okay, so this is called hard negative sampling. Let me just write it down. The question is like, how to sample better negative examples or better noisy or negative samples so now this is called hard negative mining. Hard negative mining, where given a particular sample, okay, how do you make it hard, in the sense that how do you ensure that that this negative sample is actually contributing to learning? There are multiple ways. One way to do it is that given a sample, you take all the augmentations of it and call it positive. For the negative samples, you do for every sample that you get from the data set. Okay, and please note that for the case of methods like SimCLR, the noisy samples are actually the samples from the data set itself that does not correspond to the augmentations of the given input sample. I hope that is clear. Is that clear? Let me write that down. What I mean is, in methods like SimCLR, the noisy or the negative samples are the points from the data distribution that are not the augmentations of the given input sample. So that way it slightly differs from the noise contrastive estimation, in the sense that the in distribution samples are taken to be the one that one they taken to be a sample and its augmentations, The out of distribution samples are taken to be a few randomly sampled points from the data set itself. Right. So example is, right, I mean, suppose you have an image of a digit 1, then the positive examples are its rotation and the masked version of it, and you have the noisy version of it. All of these are taken to be these are positive examples or in distribution samples. Okay, and you take the images of, let's say, 2, 3, 5, etc. All these are taken to be negative examples. And then you learn to classify between these two in a K-class classification setting. So this is also called as the anchor point or the data point at over interest, okay, of interest. So all the contrastive learning or self-supervised learning techniques would learn to classify between the samples of positive and negative examples. Is this clear?
But in this current context, we do not have the labels, right? So that's why
we
are doing a random
don't.
sample.
Exactly. So now, see what might happen, no, like one particular sample from the same class might creep up here, right? That's why you need a large batch size. That's what I'm saying. Now these examples have to be negative enough for this to work because they have to actually come from PN. Now that's why if you have a very large batch size, then the likelihood of having samples not from the same class or semantic label as that of the anchor point is less. Is the idea. All right.
So you need some kind of balanced data set here, right? As well.
Not balance. You need I mean, you can say balance, or you need a lot of negative samples. That's all. Okay. Now, any questions so far? So this is shown to be very powerful. As I said, no, SimCLR, etc., would reduce the dependence on the supervised, labels by a drastic amount of reduction is there. So examples of this approach, contrastive learning approaches in the image space, you have methods like SimCLR, or you have MoCo, and there's this thing called JEPA. I will talk about it. Okay. In the space of NLP, all these models such as BERT and what is the other thing called? It is word-to-vec. All these are variants of this NCE and InfoNCE. Okay. You
So
take,
how about clip?
Clip is also there, but clip is for it's for
cross-modal.
It's for multimodal data. But the idea is exactly the same. I can add it. Yeah, I will write it. So for speech, you have the wave-to-vec, and for image plus text, you have what does this clip stand for? I keep forgetting that. Contrastive pre-training for images and language, is it? That's what it. Just opening the clip paper.
Contrastive language image pre-training.
Yeah, contrastive language image pre-training. Okay. Now that we spoke of clip, no, maybe I can also talk about it. So you know how it is done, clip. So now there is the objective is to learn the representations or encodings jointly between the image and text modalities. See, this can be extended to any multimodal thing, okay, text. modalities. How is it done? You take two networks. So one we call as f theta, the other you call as g theta. This is the text encoder, and you have the image encoder. So this will take text as input, and this will take images as input. Okay, what they do is they take, so for this you need to have pairs of images and text. Okay, the data that you have is, you have images, you have an image comma text, that is the kind of data that you have. Okay, now you need the pair? I don't think you need the pair.
We need the pairs. Yes.
Yeah. Do we?
Yes, very much, and in very large numbers.
Let me just think about it. So contrastive pre-training, you have the, hold on, let me just see.
In a given batch, there is a set of images and their captions.
You need the corresponding captions also, no?
Yes. And the only thing is in that.
Yeah, you do need pairs.
I mean, it has to be a set, and in that set, whatever belongs to that image, that only those dot products should be maximized and all the others should be minimized.
Yeah. So what is done is, I'll tell you. Yeah. You do the same thing, no? For every text you get, and I'm just, yeah. What will happen is, for text, let's say that you get some T1, T2 corresponding to some Tn. There are embeddings for n possible texts. And similarly for images, suppose there are n images, right? You get image 1, image 2 up to image n. Okay, so you take n embeddings from the n embeddings from the image encoder, n embeddings from the text encoder. Okay, then you have an n by n matrix of embeddings, right? So this is, let's say that this is the text dimension, and you have this is as the image dimension. Okay, so what does this tell you? This will give you along the diagonal, right? This will tell you the inner product between the image embedding with the corresponding text embedding, isn't it? Now what you need is maximize the inner product, or rather this itself, no, is the inner product matrix. So let's call this matrix, let me write it down, hold on. Let's call this as IP. Now IP at I comma j is the dot product between the ith text embedding and the ith image embedding and the jth text embedding. Okay, the objective is to find theta and phi such that it maximizes the diagonal of IP, right? And yeah, maximizes this divided by and take the sum of all this. Hold on. Sum over all I, you have diag of IP divided by off diagonal elements of IP. That's all. So whenever you get the pair of you get embeddings in such a way that the inner product between the image and the corresponding text is maximized, and everything else is minimized. You need zeros here, you need maximum values here. That is how we are trying it. So now finally, after you trying this, what you can do is you take the image, okay, and what do you get? What do we need? We need an embedding, right, corresponding to a pair of text and image. That is how we have done it, isn't it? Now, when we want to do, let's say, prediction, what do? We take an image and give it to the image encoder. We get the image embedding. Okay. Then what you do is you take n possible candidate text, pass it through the text encoder, and get the text embedding. And you take the inner product of all those text embeddings with the image embedding and see which one fires. And that is the caption corresponding to that particular image. And that's how you do zero-shot prediction. Right? But as you can see, all this is actually noise contrastive estimation, isn't it? Different ways of doing noise contrastive estimation. So I encourage you to look at all of these. Okay, I mean, SimCLR we looked at. JEPA I will just talk about it in a while because I've asked you to implement this. BERT we will cover it in the next class. Wave to wake for speech is again what they do is they take the speech signal, mask it and create the positive and negative examples, and solve a contrastive learning task and get the representations. See, in fact, I was working with like one of these like insurance brokers. I mean, there is this company called Policy Bazaar, right? I was solving a research problem for them. So they were building automatic speech recognition systems for their customer centers, call centers. So they had built a supervised ASR. So when we tried wave to wave kind of approaches, okay, what happened was their dependence on supervised data came down by 85%. They could achieve the same performance on ASR by using only 20% of the supervised data. So these are very, very powerful methods, the contrastive learning methods. Okay, fine. Now the last thing that I wanted to talk about is this joint extraction of this is one thing that this guy Jan LeCun keeps talking about every day, no? It's called joint embedding predictive architecture. What they do here is they avoid the need for negative samples. Okay. What they do is the following: they take an image, okay, and by the way, they use what is called as a vision transformer as the backbone model. So I will teach transformers in the next class. Then I will talk about vision transformers. Now the idea is, suppose you have an image like this. Okay, what they do is they take random patches. They cut out some random patches from this image and call those patches as target patches. Okay, and all the other patches which are here, they create some other patches from the region that is outside of the target patches and call them as context patches. Okay, the task is to predict the target patches given the context patches as input. That's all. That's all this JEPA does. Okay, and they claim that if you do this, then the performance that we get is much better than most of the existing contrastive learning methods. Let me just show you that. This is what I have asked you to implement. Okay, so when you don't have to do it using vision transformers, you can actually do it using CNN. Do you see this figure now? My screen and figure 3. Can you confirm if you see my screen?
No, sir, not visible.
No, sir.
Not visible. Yeah, I will take questions in a while. Now, do you see the screen?
Yes, sir.
Yeah. This is what they do, right? They given an image, they divide the image into non-overlapping patches, non-overlapping patches, and they randomly take some patches as target patches, okay, and then take some other patches as context patches. Now the task is that if you are given context patches, they have two encoders. One they call as context encoder and target encoder, which share the weights. Now, given the context patches, the task is to predict the target patches. That's why they call it as the predictive architecture. So, what is to be done? Yeah, so the image-based joint embedding predictive architecture uses a single context block to predict representations of various target blocks originating from the same image. Of course, they don't predict the target patch image at the image level, they do it at the the embedding level. Okay. What's interesting is that all they use is a squared error loss between the true target and the predicted target. That's all. It's extremely easy to implement. So look at this figure. So the original image, you have this context and multiple targets. What they do is they give the context image as an input to a VIT for the context encoder, and they want to predict the embeddings corresponding to the target patches, and they simply use an MSE between the predicted target embedding and the true target embedding. Is it all right? See, it actually makes a lot of sense intuitively, no? See, it's like, suppose I give you this image, okay, and ask you to predict this. You are implicitly learning how to complete this dog phase, isn't it? Do you get what I'm trying to say? Right? So that's why they say that this thing will learn implicitly the representations that correspond to the underlying data set. Of course, as I said, the base for all this lies in noise contrast estimation. Okay, questions? It's yeah, Sarvesh.
Sir, in the assignment, we are asked to implement IJEPG. So it is a typo, right?
IJE?
PG. In the assignment,
No, yeah,
it
it
is
should be. Yeah, of course, yeah. Yeah, Aditya.
So when choosing the patches, they are completely random, or there is some
They are random. They are random.
absolutely random?
They are random,
And
but what they do, no, they will ensure that the patches for the context and the target are non-overlapping.
okay. And so, what percentage should be context and what percentage should be target if
Yeah,
you're
yeah. See
choosing an
that
image?
that is actually a hyperparameter, okay, and they have experimented with multiple of them.
Okay. Thank you, sir.
Vivek?
So in the IJPA method, how does the decoder and encoder look like? Like what
there is no decoder,
technique
no?
is?
There is no decoder. There are two encoders. One is the context encoder. The other is called the target encoder.
Then what are we learning there? I mean, what is learned? Is it a network?
The network, no? The encoder. There's enough theta network that would take a pair of, that would take a patch as an input and gives you some vector as an output.
Okay, fine. Only, okay, so it's not generating anything.
It is not generating anything. No.
Okay, fine.
Sir, in assignment,
And you can say that there is also a predictor, right? Which will do is that it will take the what they use for f theta is a vision transformer. So this transformer would give you the embeddings. Okay. They also have a predictor network that would take these embeddings, right, from the true target patch and predict
predict the entire image with the filled in.
Not the image. It will predict it will take as input the embeddings corresponding to the context. Yeah, embeddings of the context is taken as input, and it will predict the embeddings of the target.
Okay, without ever having to generate anything, it can.
There is no generation. There is no generation here.
Okay.
So there are two encoders basically. Let me just show you the figure again. Hold on. Is my screen visible?
Yes.
See, there are two encoders. One is called the context encoder and the target encoder. Okay. So what will give is this context encoder will give you a vector. Target encoder will give you another vector. Right?
Right. Yes.
Now, there is another network called the predictor network. What would this predictor network do? It will take the embedding corresponding to the context encoder, right? And predict the embeddings of the target encoder.
Yeah, embeddings of the target. Yeah. Okay,
embeddings of the target encoder and the loss for this G, right? So basically, how does the loss go? So there are two networks like this, f theta and f theta cat. Both of these are vision transformers. The context network will take some patches from the context. It will take context patches. Target encoder will take target patches. So you get two embeddings, right? Corresponding to target and the context. Now you take a predictor network that would take as input the embeddings output of the context encoder, okay, and predicts the output of the target encoder.
Okay. Yeah.
That clear?
Yes. Thank you.
There's an L2 loss between them. That's what you need to implement. As I said, no, for your implementation purposes, you can either use a vision transformer here if you can. Otherwise, you can use a simple CNN also here, no problem.
Okay.
So do we need two networks here to be trained separately?
What is done in practice is that they take. You actually need two networks, but you can share the weights between them. You need one network for target encoding, the other for the context encoding. Yeah. Okay, so great. I think we took a lot more time than usual. Okay, so that's it for today. We will reconvene again next week.
Sir, one question.
Yeah.
In question number 9, it says distilled the above resonate on a small sized MLP.
Correct.
What do we mean by distilling it?
Yeah. Not taught you distillation, right? Yeah.
So take a smaller network and show it a lot of.
No. I have to teach distillation.
Right. Okay.
Let me do it next week. If I do it next week, then I have to extend the assignment deadline for one more week. No? Distillation is a small topic that I wanted to.
Sir, that should be helpful, sir. That should be helpful.
I will do that. Okay, no problem.
But sir, it will land in our exam time.
Meaning the assignment deadline you are saying, huh?
Correct.
That's okay, no? I mean, I'll just give you maybe one more week till 30th.
Yes, sir. Yes, sir. It's okay.
Till 30th should be okay, no? Let me do it right away. So that
Yes, sir.
Assignments. Because anyway, I'm grading it on like the first week, right? So assignment 3, edit. Please remind me, next class I need to teach distillation. I completely went off my head.
Then when will be the VIVA?
First week of December.
Okay.
Sir, one
Done. I
generic
just
question.
read. Yeah.
You said you worked on a solution with Policy Bazaar. So when you work a solution like this, do you drive